Okay, I started recording. Okay. Alright, so welcome to the 2CO3 full course review. My name is Pavlos. I'm sure you guys have seen me before from the other help sessions. I will be the main CSS rep doing this help session. This is actually one of my favorite courses. I like that it's fairly practical in the not that other courses are not, but this feels like immediately practical to the real world. And I just like the theory part as well, with proving time complexities and things like that. I think it's very neat. And it has real world implications. Again, algorithms run the world. So exploring the theory and how we can make things potentially faster, that's a very exciting thing. Okay, so just a quick outline. So I'm going to go through some fundamentals. So orders of growth, correctness, recurrence relations. And then sorting, which I'm going to use other slides for. I'm going to use the algorithm for. Actually, get my pointer. Okay. Yeah, I'm going to use the algorithm for textbook slides for that and for searching. And then I was able to get my graph algorithm slides done, so I will do that one too. Yeah, so let's get into it. Right, so this is going to be like a lot of high level stuff. I'm just going to skim over to give you just like an overview. Okay, so again, orders of growth. This is just understanding the family of functions your algorithm's running time is and how it grows with input size. So essentially, all you need to know for this is like how to compare different orders of growth, or like what they are essentially. So basically, if you go down this list, this will be essentially it'll be slower the more you go down. So again, you have constant time. That's the best you can do. So these are just like accessing an array, arithmetic operations, things that don't grow with the input size. It's just constant. And the next best we can do is sort of logarithmically. So this is like your binary search, splitting things in half. It's very efficient. If we can even get something close to these for any algorithm, that's a very good thing. Yeah, for like sorting, you're going to have basically this. I'm sure you've gone through in the course that you can prove that for comparative sorting, the best you can do is here. So for sorting, you have a class that's going to be like from here to here, essentially, for sorting. Yeah, so just know the order. It's fairly simple to know the order. Just know that polynomials are pretty large, and then like linearly, if you're going to multiply something by like a logarithmic factor, that's going to be more than just a linear. And then yeah, that's all you have to know. Just know the order of these, and then perhaps some of the examples where they pop up. That's going to be all on your formula sheet again, so this one's not too critical, but just know the order they are in. So yeah, so often we want to make, because again, in computing we often have to do a lot of operations on a large input. So for example, you want to sort a large, extremely large set of numbers, so like billions of numbers or millions of numbers. So we like to describe like an algorithm's running time in terms of bounds. So these are common ones. So this tilde notation, this is actually, it's a very uncommon, like this is basically just from Algs 4 textbook. You don't really see this one much. This is basically a very precise, like asymptotic description. So basically it's like doing big O, sort of, but you keep the constants. So you can have something like 3n squared plus n, and then you just keep the biggest term with the constant, so that would be tilde 3n squared. So it's just a bit more precise description. Again, we have the limit definition here. So basically it's just saying the highest order term's gonna dominate there, and then it's gonna be 1. Yeah, so we include the constant factors there. So these big O, big omega, big theta, again, this chart, this is from ALX 4, this chart. I love ALX 4. This is the textbook we used last year. Usually we actually just call this theta because, at least in this course, there's no little theta. But yeah, here they just call it big theta because it's just a capital Greek letter theta, so that's why they call it big theta. But you can also just call it theta. There's also little o and little omega, but they're not as important for right now. So basically, just to understand what these mean, I know we have this very formal definition about constants and constant factors, but basically I'll just draw it out. So say you have a function f of n. So this could be the, and we'll be very low key. We'll just say this is effort. So like computing effort, and then this is just your input size. So here we have a nice linear function. So I can say something about how fast, I can make statements about this will be no slower or no faster than. So the big O notation is basically saying, so say I have another function. Let me get another ink here. So say I have a quadratic function. That one goes up like that. So sort of tie in where this comes from. So we have this point here. We'll call this n naught. And then we can see that from this point on, we'll call this one g of n. There's going to be some, well, it's going to be n squared. So we can see from this point on, our original function will be no slower than quadratic, because this one's going to blow up all the way up here, and we're still going to be going here. So we can say that f of n is going to be O of n squared, because it will not do any worse than quadratic, because linear is much better than quadratic. But we can also say something about the lower bound too. Yeah, so this n naught point here, that's just saying where it, like where the proposition holds for like it always being less than or equal to. So f of n is always less than or equal to n squared at this point here. But we can also say something about a lower bound. So say we have something logarithmic. So it actually, I believe it goes something like this. So you can see at this point here, we'll also call this n0. The linear function will always be greater than the logarithmic function. So that's basically saying it's big omega. So it's going to be no faster than logarithmically at this point on. But actually this is all sort of unnecessary because, again, I can pick any function that's just bigger than f of n. So you actually want to be as tight as possible because, as you know, before quadratic class, we have the linear-arithmetic class. So I can actually say something, I don't know the exact shape, but it's going to be something like, perhaps this, something like that. So what I'm trying to get to is when you describe an algorithm, so this could be n log n, which is, this is also going to be a higher order than linear. The theta is sort of the ideal scenario, because what if I just say let me clear this eraser. So these are all true from this definition. Like, we're always going to be bigger than linear, but it's not precise enough. So that the big theta is sort of the ideal scenario. So if we have, I can just draw another linear function. Say this is, I don't know, 2n. And then I can draw another linear function. Where is it? Say this is 1/2 n. And this is much precise. Now I can say, since I have a function that's always on top, so that's going to be my big O piece, and I have something that's always under it. So now I can just say, this is tightly linear. Like, this is the best I can do in terms of describing this thing. Because essentially it's just a straight line. So I can just say it's always going to be a straight line. That's what big theta is. You're just saying it's always going to be around linear. Yeah, so that's tight bounds. There. Okay. Right, so now we're going to get into case analysis. So, especially for more complex algorithms, your inputs could be different. For instance, a sorting algorithm, you might have perhaps the order the thing your input comes in, the nature of it. Is it already sorted? Are they all randomly sorted? Is it a random distribution in your array? So depending on that, the nature of your input, we can have cases. So all you can think for cases, so for like worst case, like all these cases are different functions. So we'll look at a simple case analysis of linear search. Yeah, so worst case is, this is the worst input that you can have. That gives you the worst time complexity. The best case is the most favorable input. An average case is actually a bit harder to derive. There's actually some algorithms, some sorting algorithms, such as shell sort, which I'm not sure if you guys have done. Shell sort is a very interesting algorithm, and the average case has not been discovered yet because it's the nature of that algorithm just makes it very hard to derive the average case. And one reason is you have to have an assumed input distribution. So you need to assume something about the inputs, which is very hard to do for very complex algorithms. But for linear search, average case does exist. So yeah, this is like for typical input. So on average, if you take in stats, you can sort of think of this as the expected value, because if you're assuming there's an input distribution, you can, this is a bit of high level stuff, but okay, so this is going to be a simple case analysis of linear search. So linear search is you have an array of numbers that's already sorted. So let's just do something like 1, 2, 3, 4, 5. And you want to check if your target is in the list. So we just want to search for it sequentially. So you're going to start at the beginning, go 1, 2, 3, and you're going to go through the list and check. So the best case condition is, what if your target is just the first element? Then that's going to be constant time. You're just going to do one array access, which can be done in linear time because you just have to fetch it from memory. That's the best case. So if you think of the best case as a function, you can have the time it'll take is just going to be 1. And then we can say asymptotically, it will always be 1. That's very tightly bounded. There's not much variation in that. It's always just going to be constant time. For worst case, so worst case could be perhaps you're searching for something that doesn't exist, so you're going to have to go through the entire list. Or perhaps the element is at the is the last element. So you're going to have to go through the entire list. If the list has n elements, you're going to have a time complexity of linear time. So you're going to go through the entire list. And that will always be true, so that's why we can tightly bound it as linear. Now the average case analysis is a bit more tricky. But if we assume that target position is equally likely, so if it follows a uniform distribution, we can say it's going to be, your target on average will be in the middle, which would still be linear time because we're going to ignore the constants. And just one note, just as computer scientists, this is very important. So we can use any of these notations to describe any of these cases. I think a very common misconception is that you can only use, this is a misconception, is that big O can only be used for the worst case analysis. But I can say, because these are just properties of a function, and we have 3 different functions, so we can actually, because in essence, this is a statement of big O and omega, because you're saying in worst case it's going to be constant time, so that's a statement about big O. And I can also say it'll be no faster than constant time. So just because you see big O doesn't mean that you can apply any of these notations, because they're just properties of functions. You can apply them to any case, to describe any case. Does that make sense? Okay, just wondering, have you guys talked about amortized analysis? This is a very quick thing I'll go over, and it'll be useful to understand some of the time complexities of other algorithms, but essentially sometimes we want to know, say we're doing a different sequence of operations, so sometimes you want to know what's the average cost. Okay, yeah, okay, nice. So a good example is the vector, or we call it dynamic array. So in C++ we have something called the vector, which is just an array that resizes. So again, so we want to know how expensive is it to insert n elements, because as we know with regular arrays, they're fixed size. So once we get to as big as it can go, we're going to have to copy those elements to a bigger array. So we're doing insertions to insert our elements, but we're also going to be doing resizing. So on average, if we take a limit, on average, what is the cost of pushing to this vector data structure? So again, pushing to an array is going to be constant time. However, occasionally, we're going to have to resize the array. So we're going to double its size every time it's full. So that's some, and then we're going to have to copy all the elements into the new array. So we're doing pushing, but we're also doing resizing. So if we insert n times, so that's just going to be n times 1, essentially, which is going to be n. So we're just inserting n elements, that's going to take O of n time. But we're also doubling, so we're going to have this summation, which also converges linearly. So that's, and then our total cost is going to be the cost of us inserting and then the cost of us doubling, which is going to be O of n, because the sum of O of n and O of n is going to just be O of n. Because when you add time complexities, you take the maximum one, and they're both the same. And then we just have how many operations are we doing? We're doing n of them. So this will sort of converge to constant time. So basically what this is saying is that as we double, like, on average, it's the push that really matters. The doubling it sort of gets smoothed out. So we're smoothing out expensive operations. So this, on average, we're doing a constant time operation. So that's good to know. Yeah. Okay, so this is the correctness algorithms part. So this will probably appear on many of your questions on the exam, or sort of a flavor of correctness of algorithms. So this is what I sort of concluded from Helling's notes. So I'm going to go through it. So, and again, you've sort of been doing this in 2LC3 as well with your while loops, but it's a bit different, but it's about the same in theory. But so algorithms is correct if it always finishes, so it terminates, and then you get what it's supposed to do. So this is called partial correctness because you get what you do, but you also need to know if it ends. And then we can classify algorithms into two classes. So we can do things iteratively, so that's using loops and repetitive steps until you meet a condition. Or you can do something recursively, break things into smaller subproblems until you terminate through the base case. So with iterative algorithms, you're using variables for state, and then recursions can use the call stack. So my example is going to be calculating the Fibonacci number. And you might need induction for either of these. Yeah, so the example we'll be doing later is the Fibonacci number, correctness of calculating the Fibonacci number, because you can do it iteratively or recursively. Right, so for iterative algorithms, so these are ones with loops, while loops. You've done correctness of algorithms in 2LC3. So perhaps you can sort of map that. I know it's very hard to understand 2LC3, but you have some context. Okay, so we need some info first. So we need to know what must be true before the algorithm starts, and we need to know what must be true at the end of the algorithm. And then if your algorithm has a loop, you can define the loop invariant. So the loop invariant it's the property that it's going to be true before the first iteration, remains true at the start of each iteration, and then together with the loop's exit condition ensures the post condition holds. So this is sort of the core of the correctness. So this invariant is going to help you get to your post condition. And a note about the invariant is, since a lot of things are changing in the middle of the loop, it might become temporarily false, but as long as it satisfies these, it's a valid invariant. So this helps ensure the post condition holds. So that is, we're going to get what it's supposed to do. That's the whole point of the invariant, is to help push it towards the post condition, or correctness of the post condition. So you can use induction for an iterative algorithm to prove it holds. So there's three things you need to prove for it. First, you need to prove the invariant holds. So this is some expression. It holds for the base case. And then you also need to prove it holds after each iteration, which is going to be sort of like your inductive step. And then you also need to prove termination. So you need to define a function that shows that it terminates. So it's going to be like a decreasing function, like each iteration. So yeah, I think this is better explained through an actual example. So let's go through that. yeah, I shouldn't get my slides done here, so I'm just gonna sort of explain what I got from chat, but oh, I will try to explain this the best I can. Okay, so so here's our precondition. So we have an iterative Fibonacci algorithm, so it's going to calculate the Fibonacci sequence for a given n, or the Fibonacci number. So we can see that we have some base cases here. So A is 0, B is 1. But our precondition is that we have a number that is greater than or equal to 0. So n has to be a natural number. And the postcondition is that we properly calculate the Fibonacci number, as shown here. Okay, so we're going to be doing, so we've done 1 and 2, now we have to do 3. So to find, prove the invariant. So here we have yeah, so our base cases is going to be A is 0, which is going to be f of 0. Then we have P is 1, which is f of 1. And then, wait, 1 sec. I don't think I actually wrote the invariant on. 1 sec. Okay, yeah, it's actually right here. Sorry, I couldn't see it. Okay. Yeah, so our invariant is going to be that, so we're going to say something about A and B, because obviously that's going to be important for proving that it's going to calculate the Fibonacci number, because A and B essentially determine what happens at the end. Yeah, so we're going to say f of I is the ith Fibonacci, and then B is going to always be 1 ahead of it. So that's our loop invariant. So that's a pretty good invariant because that's essentially the definition of Fibonacci. So if we can prove that's true, then that will prove the correctness of this algorithm. Yeah, so these are our base cases. A is 0, B is 1. So you prove that's true. And then see here, we can just sort of just use just basic arithmetic to prove that for each iteration. So this is our maintenance step. So we have to prove for each iteration it's going to calculate the right Fibonacci number. And that's just through the definition of Fibonacci here. Yeah, so then we get maintenance done. And then we can easily prove termination through this bound function. So bound function is n minus I, which we can get from here. Yeah, so we can see when n equals I, this will terminate. Yeah, so this is a very simple example. And this one sort of just comes from the definition of Fibonacci sequence. That's sort of how we get this done. So again, just know when you do these sort of correctness proofs, just ask yourself, what's my base case? Well, the base case has been sort of defined here. What's my bound function? Where are we going from? It's given right here. Yeah, and then just reason about what's in the middle. So yeah, this is sort of the definition of Fibonacci. Yeah. that's the correctness for this one. I think the recursive one is a bit more neat. So again, we're going to use induction because induction is really good on recursion. And things are essentially the same. Again, we have our base cases. So again, ask yourself, what's my base cases? So we have 0 and 1. And we see those will terminate. And those return the right Fibonacci numbers for those. So that's good. And then we just use the inductive step. Again, for this one, it's just proving the definition of Fibonacci, but that's sort of my idea for this example. It's just to show you, in essence, a lot of these will just come down to basic induction proofs. So if you just know how to do induction, which you've done in 1DM3, these should be fairly simple. Again, you're gonna have these for like sorting algorithms, which we can go through later. But yeah, just remember sort of the steps of what you're doing and sort of the intuition. And yeah, so here, this is like what's actually happening on the call stack. So we start with the number we want. So we're going to find Fibonacci of 5. And those will branch for each. So we're doing n-1, n-2. And you can see here that those will eventually go down, and then we will terminate when it gets to 1 and 0. So something neat about this implementation of Fibonacci is, okay, let's sort of analyze the time complexity of this one. So this is the time complexity of recursive algorithms. So how many let's try to make a statement about n. So we're given n, so for each of those split into 2, and then those split into 2. And something about this is we're not, and you'll explore this in 2xc3, we are actually computing the same thing multiple times. So Fibonacci of 2 is also being done here. So we're actually reusing things multiple times. And a more optimized version of this would be using something called dynamic programming, where you can store the previous results in like a map or a dictionary. Yeah, you can see here. So how many times will this split? Well, it turns out that this implementation of Fibonacci is going to be O of 2n. And that's sort of convincing because for each of these, we're splitting into 2, each time until they're all finished. So that's going to be 2 to the n. There. And you'll learn this in 2xc3, we can actually get this to linear time using dynamic programming, but that's for another discussion. Yeah, so so my advice for you for these correctness proofs is just ask yourself, what's my base case? And then ask yourself, make your induction hypothesis, and then try to prove your thing through induction. And then ask yourself something about the input. So you'll probably be given the precondition and the postcondition. Yeah, that's my advice for these questions. Yeah, so I didn't do much of this in my 2CO3, but yeah, that's from what I've gathered from this. That's my advice for these sort of questions where they're asking for proofs of correctness. Yeah. Okay, so recurrence relations. So recurrence relations are used to find the time complexity of recursive algorithms. So I put a little chart here. These are some very common ones. So a general form for a recurrence relation is going to be like you're going to have base cases, because obviously this is a recursive sort of formula. So you're going to have things where it's going to have to terminate. So you might have something like t of 0 or something like this. It's going to be, I don't know, 1, something like that. So just something that shows that it's going to terminate, because you can't really compute it otherwise if it's not going to terminate. But it's going to have sort of a general form. So let me get a different color. So sort of the core of your recurrence relation is you're going to have sort of A and then T of n by B. And I'll explain what A and B are. And then you're going to have plus some just function about the effort, or like how costly this operation is at this n. So perhaps I can just explain what A and B are from an example. So this one's for binary search. So again, for binary search, we're splitting the array in half each time until we find the number we want. So B here is 2. So B is it's basically saying the factor of like how many times do you want to split the subproblem. So we're going to split it in half each time. And then here, this is the amount of effort for this step. So this is probably just a constant operation. So this could be like an array access and comparison. So that's just for this term n. So again, and then you're going to have this, and then this is going to recurse. And then you can sort of make a statement through evaluating the summation you're going to get. And then you'll get that it's going to be around log n, because we know it's going to be log n, because how many times can you split the subproblem until you're going to get to your base case? Well, that's going to be, by definition, log base 2 of n. Yeah, so sort of you have to reason about what the recurrence relation is saying in terms of like this formula. So here we go again. Merge sort. It's very similar to the recurrence relation of binary search. They're both splitting something in half. So again, B is 2. So we're splitting something in half, but we can see that merge sort is has a 2 here. So basically you're doing this twice, because again, you're splitting them in half on both sides. And then for each level, you're going to have n comparisons. And we can use the same reasoning for the log n part, and how many times you're going to add this. We're going to add log n times. So that's how we get the time complexity for merge sort. That's sort of the very shallow explanation, but A, what I'm trying to get at is A is how many times you want to do this recurrence, and then B is how much do you want to split the subproblem into. And then f of n is the cost of the current step. And then you sort of reason about what the formula is saying to get your approximation. Again, here, insertion sort, we have the prefix array, and we're knocking one off each iteration. And yeah. And actually, in my course, I didn't do recurrence relations. I believe this is something you do in 3AC3. So this is also a new topic for me, but this is, yeah. Okay, so sorting. I just have some remarks to make about sorting, so I'm not going to explain what each sorting algorithm does, because looking at your practice exam, there's not much like like, I don't think you're going to have to code merge sort, because again, you can just put that on your formula sheet. So I'm not going to give a question like that. What they're going to give a question about, and this is sort of the whole idea of this course, is, again, we have all these wonderful algorithms that's been around for a long time. The question is, how do you map those algorithms to like a problem, like a practical problem? And what constraints do you have that's going to lead you to the conclusion to use a certain algorithm? But some remarks I'll make about perhaps what to put on your cheat sheet is you might want to record on your cheat sheet sort of what these terms mean, because I remember on your practice exam, I believe the first question asks about these things. So stability, this is saying that when you sort something, things in a relative element, in a relative position, they'll be in the same order they came in. So for instance, say you have like a pair. So you have like Bob, and then say Bob has some value 3, and then you have I don't know, Joe, and he's also 3. So say you're sorting it by this value here. So we're going to be sorting by the values here. So when the sorting, and so you have like a bunch of other elements in this list. Basically what stability says is when they're sorted, when you sort the thing, your final list, Bob's still going to be first, and Joe will be after Bob. That's what stability says. So you're not going to swap equal elements. I believe in your practice exam, the proof for the stability question was there was a piece of the code that was swapping equal elements. So that would show that stability is being violated, because you want to make sure they come in the same order, or they're sorted. The final thing comes the order they came in. So stability is something. I'm gonna give a lot of resources for good charts for like all the algorithms, and if there's stability, they're in place at the end. But yeah, record for each algorithm if it's stable or not. And in place is a statement about how much memory it uses. In my course, we defined it as and it's fairly standard definition. So if you use more than log n memory, you're not in place. So yeah, just again, for sorting algorithms, you're going to see the algorithm, and then if you see like auxiliary arrays, so if you see new arrays being created that is not the input array, you might suspect that that algorithm, if they're asking if it's in place, it might not be in place. If you're just seeing variables being defined, okay, those are all constant space operations. So yeah, when you get, because I'm pretty confident that your first question on the exam is going to be a sorting algorithm, probably something close to an elementary sort, or it's probably going to be like an insertion sort, or maybe selection sort, and you're going to have to prove some properties about it. So if you're seeing just variables being defined, so if you are just seeing like I equals this and j is that, and you don't see anything about like bigger data structures being used, then if it asks if it's in place, then you'll say yes, because you're just using constant memory. And optimal, this is actually a very big thing. So an optimal, so if you're doing a comparative based sorting, so you can prove that any, I'm not going to do the proof now, but you can prove that any comparative based algorithm can do no better than n log n time. So again, on your practice exam, it asks if it's optimal. So if your algorithm is not this time complexity n log n, it's not optimal because it doesn't reach the lower bound. Yeah, if you're given like a sort of elementary sort of question where it's probably gonna be like a quadratic sort. So yeah, watch out for like algorithms that look like a elementary sort. So like if it looks like insertion sort, or if it looks like selection sort or bubble sort, you're probably not going to be optimal. So yeah, watch out for that. If you see something that's like merge sort, then yeah, watch out for it might be n log n, so you can say it is optimal. Yeah, and just one little remark about optimality. We actually talked about a lot of this in our last year in 2CO3. We actually did a whole section on string algorithms. If you're not doing comparison, there's an algorithm called radix sort that can actually do better than this bound, which is very interesting. Yeah, if you're interested about that, you can read section 5 of algorithms 4. That's just an extra remark I would make. So I'll just say better does exist. For non-comparison. I'm just gonna use a short form. There, yeah. Yeah, if you want to learn about that. Yeah, okay. I do have a chart here. Okay, so this is the chart I recommend you put on your cheat sheet. I know your formula sheet has the time complexities, but again, this one has remarks on the side. It has in place, stable. You can ignore cell short in this code here. Yeah, just having these remarks here can be helpful. It also gives the time complexity with sort of the tilde notation where it keeps the coefficient. If it asks for just like an order, like an asymptotic notation, like a big O, just get rid of these constants here. Yeah, and at the bottom, this just is saying something about an assumption about keys being distinct. So that's for heap sort. Best case is linear time. Yeah, so for your cheat sheet, yeah, just know which ones are unstable in place. That might help you map that onto algorithms that look like, for the first question, if they give you an algorithm, that will help you map that onto the actual question. And you might also want to put the actual code for a selection sort and like all the other algorithms if you feel like it's necessary on your cheat sheet. That might help you pattern match the algorithm they give you, assuming that the first question is sort of like a sort of properties of sorting algorithms question. Yeah, so that's my advice for that question. So okay. Oh, I have a question here. Wait, how come at most? Okay, yeah, so for in place, so I will go through the in place. So these algorithms, selection sort, insertion sort, bubble sort, quick sort, and heap sort, they don't use, so merge sort uses an auxiliary array, which uses, I believe it's going to be linear memory. So it has an array it copies the merge to. So that it's creating a whole new array. Quick sort, heap sort, like all these other ones, they are in place. So they don't use this much memory. So like these ones are just setting variables, and then these have like the priority queue, and these don't use like this uses less than or equal to log n memory. It's not saying that it uses log n memory. It's just a statement about like the maximum amount of memory So all you have to know is that merge sort uses like an additional array of memory, and then all the other ones don't. Yeah, that's what I'm saying. Like if you just see variables being defined and not like another array, that's copying everything, it's in place. And yeah, merge sort is the only non-in place one. And that's another remark about merge sort. So merge sort is a good example of time-space optimization. So perhaps if you have a computer that has memory for it, it might be a good idea. Again, it's going to depend what you're doing, but we are giving up memory for a guaranteed n log n sort. So see, quicksort, we can get n log n. It is possible if our pivot is good. However, again, it depends on the pivot. Merge sort is sort of like we're using that additional array to always guarantee that we can split it in half perfectly. Quicksort, the pivot or perhaps the input, like if you have like a really bad scenario where your pivot, if you have like a sorted array and the pivot's at the end, for quicksort you can actually have a quadratic time. So we're not making a sacrifice for memory and we're relying on a pivot. That is causing quicksort to have a quadratic time, while we sacrifice memory in merge sort and we get a guaranteed n log n time. So that's sort of we call it time memory or time space trade-off. So yeah, that's something you'll also explore in 2xc3 next semester. Question 1 is going to ask for a double invariant. If question 1 is going to ask for double invariance for outer and inner loop, would it be safe to assume that it narrows the possible sorts and exchange sort? Yeah, that is, I believe that's a good assumption to make. Yeah, double invariant. Yeah, that makes sense because all the elementary sorts are going to have 2 loops. Yeah, that's a good assumption to make. And again, if you see recursion, you know you're going to have to do something like a proof that you would do like the proof, like something like merge sort. Yeah, if you see 2 for loops, you're going to probably have an elementary sort. And yeah, double invariant. Yeah, that's a good assumption to make. Yeah, and then this is from the Algorithms 4 textbook, which is the textbook we used last year. It's just a general question. Is there a best sorting algorithm? So if someone asks you in an interview or on the test, what is the best sorting algorithm? If they don't give you any other context, you say no, because sorting algorithms, there's so many that exist because we use them in different scenarios. So again, look what I was explaining. Perhaps we have a very old computer or a very small computer that just doesn't have enough memory. So you have a drone, like a very small drone or something that doesn't have a lot of RAM. We might not want to use merge sort and say this drone is calculating or maybe sorting 20 million I don't know, maybe coordinates or something, I'm not sure. But say it's just sorting something and it doesn't have memory, then you wouldn't use merge sort. So merge sort isn't always the best, because if we don't have memory, then we can't even use merge sort in the first place. Especially if you have a very large thing. If you're sorting 20 million things, how much memory does that take? It takes a lot of memory. And yeah, you'll explore this a lot in 2xc3. Yeah, so what I'm trying to sort of get at is there is no best, like general best. If one day we have the holy grail of sorting where you have check marks across the board and it's n log n, that would be the best. But we don't have that as today. We still don't know if there is a holy grail of comparative sorting. So it's going to be scenario based because of that. you're gonna explore that in 2xc3. Okay, searching. I'll go back to searching. I'm gonna go to graphs. Yeah, for this I'm gonna use algorithms for textbook slides. For that, graphs. Okay. All right. So for graphs, so we can think of a graph as sort of like a mathematical structure. So we're going to have vertices, which are like nodes. So a vertice could be like a node, and it has some value inside of it. And then we have, so we're going to have, those maybe have A, B, maybe these all storing a character or something like that. And then we have a set of edges, which is going to be how we sort of relate the nodes to each other. So yes, maybe have, so this might be our graph here. And then optionally, we can have weights. So weights are very good, again, for like shortest paths, where these could represent distance or cost, how costly something is. Yeah, so we can have weights here. We don't have to, maybe you just wanted to demonstrate just connectivity, not weights. So that's optional. And what I'm writing here is that a weight takes an edge, and then it maps it to a number. So we just have an edge here, which is, you have u and v. So just that connection, and we're going to say it's some number, like this. This has a meaning. So from here to here, that just maps it to some real number. So we have two main types of graphs. So you have directed graphs. So that is an ordered pair. So, and we denote that with arrows. So what directed graphs are helpful for is if you want to say that you can only go, like, you want to demonstrate that you can get from here to here. So I can go from u to v, but not v to u. So this might be like one-way streets. You can go up the street, but you can't go back the other way around. Yeah, so that's what directed graphs are. So yeah, so it's an ordered pair. And in this notation here, this is just saying that u goes to v with weight w. And here we have unordered pairs, so I just used a set because sets are unordered, and that's going to be in the set of edges. So we have bidirectionality, so you can go from u to v. So you can choose to not draw arrows, or you can draw arrows on both sides, but usually it's drawn with no arrows. Yeah, so this is saying I can go from A to B, and then I can also go back, I can go B to A. So that's graphs are. It's just a mathematical structure to represent this. Okay, so these are terminology. I feel like it's really important to understand terminology because perhaps they're looking for, like, they want to know if you're able to, like, express, like, your answers, like, more, like, understandably. So terminology is good for that type of stuff, and terminology is good because we use it to define things that we use to explain other graph algorithms. So we're going to need to define what is acyclic so we can create some algorithms for just acyclic graphs. So that's why it's important to understand terminology. And we use the terminology as well for the proofs for the graph algorithms. So I'm just going to quickly go through these, and then I will explain these here. Okay, so if we have a vertex, wait, so yeah, I will just put a remark that this is an undirected graph up here. And then this is directed. This example is directed. So the degree of V is going to be how many vertices can I get to from the given vertice. So if we go here, let me get my pointer. Yeah, so this one here, it's pointing at this one. So the degree of this one would be 3 because there's 3 vertices connecting to this one. And again, for directed graphs, since we're not going back and forth, we're going to have to define it a bit more precisely. So we can have in degree. So that's how many arrows are pointing at V. And then out is how many arrows point out from V. So we have this one here. So we see in degree, there's 3 arrows pointing in. So there's 3 vertices pointing in. And then there's 2 pointing outwards. So that's an in degree of 3 and out degree of 2. Adjacent vertices is just it's just the vertices that are near, that have an edge with each other. Yeah, a path is, yeah, so we'll go to path. So here's a path of length 4. If you can see, it's sort of highlighted gray here. Yeah, so a path is just an edge-by-edge connection from U to, we can say, a vertex S. So this one has a length of 4, so we have 4 edges here. Yep. Cycle is a path that starts and ends at the same vertex, and no edge is used twice. So here's one that's highlighted in gray here. So we can start, say this is U at the top here, and then this one has 5 edges. 1, 2, 3, 4, 5. So we start and end here. So that's a cycle. Acyclic just describes graphs that have no cycles, which we'll see later. A connected graph would be a graph where you can get from anywhere, starting from anywhere. So if I pick any arbitrary vertex, I can get to any other arbitrary vertex from the starting vertex. And then connected components. So here we have, it says connected components. So as you can see here, like this big one here, you can get to any vertex starting from any vertex. So this sort of blob here is connected. So all of this is connected, but it's not connected with the other sort of islands here. So we just call it a component. So if this is the entire graph, this big blob is a subgraph. So it's like a subset of the graph. So, and that thing is connected. Like these are all connected. So we call them separate connected components. And we can also describe something in terms of digraphs. So this terminology is only for digraphs. It's called strongly connected. That's just to describe that there's a directed path from a V to W, so from 2 arbitrary nodes, and then there's also a path back from those 2 arbitrary nodes. And that's used to describe what we call strongly connected components. So we just use sort of the definition of connected components, and then we just put the definition of strongly connected in front of it, and that's sort of the definition of a strongly connected component. So yeah, so now we're at digraphs here. So the connected components part is the maximal connected subgraph part. But strongly connected refers to, so we can see this 6 here. What time is it? Okay, yeah. So this 6 here, this is actually its own strong component because, so you can go from 6 to 4, 6 to 0, 6 to 9, but you can't go from 4 to 6. See, there's no way to go from 4 to 6. So by definition, they cannot be in the same connected components by this definition of V and W, W to V. Yeah, so it's sort of a more strict definition of connected components, and it's just for digraphs. Yeah. And we have tree. So a tree is a type of graph. So binary search trees, you can think of them as a graph. Those are just connected graphs with no cycles. And if you have a bunch of trees that are not connected to each other, that's called a forest. And an important one is DAGs, directed acyclic graphs. So those are graphs where, like, we'll draw one here. So a DAG is a directed graph with no cycles. So here's a DAG. The most simplest DAG I can draw with 3 vertices would be something like this. So this is a directed graph, right? It's directed because I defined directed edges. And there's no cycle. So there's no vertice here where I can get back to that vertice. Like I can't go from A, C back to A. So this is acyclic and it's directed, so it's a DAG. This is a DAG. There. But if I then put a new edge here, now it would not be a DAG anymore because I could just go around. Oh wait, I would have to complete this thing like that. I'd be able to go around and around. That'd be a cycle. Yeah, and we talked about strongly connected components. Yeah, these definitions I got from Algorithms 4th edition. They're very standard definitions, so yeah. Yeah, so there's 2 main ways we can create a graph in a graph data structure. So, and again, it depends on the scenario you're in. So we have 2 ways. Now it's your job to pick which one is the best for the job. So the first way you can do it, sorry, I have a bit of a lower quality image here, but I feel it's a good image. So adjacency matrix, so you're going to make a V by V. So this notation here, where you see like V, this is the number of vertices. Yeah, so that's basically you're making a square of vertices, like a matrix. This comes from it's like the magnitude of V or the cardinality. So that's the number of vertices. So we can sort of define a piecewise function. So if we have, this actually, this is supposed to be a V here, not Y. Yeah, so, that's a V. Okay. Yeah, so at some edge UV, if it exists, we're going to say it's a 1 in the adjacency matrix and 0 otherwise. So that's going to tell us if an edge exists. So if you go to that location and it's 0, then you know there's no edge there. So this, again, it's very good because you can have O of 1 lookups because it's going to be an array. And it's very simple. Again, it's just a V by V array. But that's also a con. It's a V by V array. It's if you have sparse graphs. So sparse graphs, I put at the bottom here. Sparse graphs. That's when you have a lot of vertices relative to edges. Yeah, it's when the number of edges is much lower than the number of vertices. So you have a lot of vertices. That v by v is going to be very big, and it's going to be quadratic. So that's going to be very big. So you wouldn't use it if you have a sparse graph, a graph that has a lot of vertices but not many edges. Another thing to note, so for it doesn't show here. Yeah. So if you had an undirected graph, you would actually have copies in the adjacency matrix, because again, it's going to be bidirectional. So say you had, we can do it up here. So if you had if you had undirected, because again, in undirected, U and V point to each other. So that means in the adjacency matrix, you're going to say UV. Let's assume they have a connection. You're going to say that is 1. So U and V. So it's going to be 1. But you're also going to say, because it's true, because it's undirected, you're also going to say at V, V has a connection to U. That's true. U, so the first one is U has a connection to V, but also V has a connection to U. So that's for undirected graphs. You're going to have copies like that. Okay, so that's adjacency matrix. So very costly in terms of sparse graphs, but very fast edge lookup times. But perhaps we have dense graphs. And dense graphs can show up a lot too. So that's why we define adjacency lists. So the adjacency list, so you're going to have an array of magnitude v, and then so for each vertice, and I'll just go to this one. Yeah. So for each vertice, that at that index you're going to have another. It could be like a bag data structure or another array of. You're going to have a collection of the vertices at which it has an edge to. Yeah. So let's look at this example here. So this is a directed graph, and we can represent this directed graph by adjacency matrix or adjacency list. I'll go to the adjacency list because that's what we're talking about right now. So for instance, for A, so at A, here it's pointing to B, C, and D. So at that index, that's what we call like an adjacency list. So at like the list is storing the relative adjacencies. So at A, we just have like a bag or a collection or dictionary of the relative connections there. So some remarks about this is, again, if you have to find a lookup, for the worst case is going to be the degree of that vertice. So A has 3 connections. So if we want to get to the D, we're going to have to do the degree of V. It's because the degree of V of the degree of A is 3. So we're going to have to do at most 3 operations to get to D here. Yeah, and then again, it's very easy to iterate over the neighbors, right? You just go to that index and then you have all the neighbors right there. And it's space efficient. We're not doing a V by V matrix. We're actually doing V vertices and then E edges for space. So yeah, so this will be really good for dense graphs where E is going to be close to V squared. Yeah. Yeah, and then I guess I'll just show an example of the adjacency for this one. So A is pointing to C. So at AC, we should have 1. Yeah, so it's 1 wherever you see a connection here. Yeah, so that's graph representation. And if you're asked to pick one, if they're giving you a problem and they ask you to represent the graph, consider how much memory you're using and consider how, like, if it's a dense graph, if the situation produces dense graphs or sparse graphs. Yeah. Are these slides shared? Yes, they'll be shared right after the session. Yeah. Are undirected. Yeah, undirected are symmetric, as I shown here. Yeah, any questions? I'm just gonna wait. Commits E plus E, not just E for the list representation. Yeah, so it's V plus E. Yeah, it's E plus V because you have where is it? Let me draw it out. Okay, yeah. So you're having V plus. Actually, I might have that. That one might be wrong. Yeah, so you have V edges, V vertices, and then yeah, because you didn't have E. Actually, I think I remember this one. Actually, might be. I'll come back to this one, but I believe you're gonna have right for an undirected graph. This might be 2E because for an undirected graph this would be 2E because at most you're gonna have just like a copy for each edge. Yeah, 2E. Yeah, I'll come back to that one. Yeah. Okay, so yeah, you still have this store bounded by E. Yes. Yeah. Yeah, because again, it's a function of V. So like how big that list will be is going to be a function of V, and then you're going to have how many edges you have. And actually this E might be 2E here as I'm describing, because you might have copies, but then it gets simplified to just E. Yeah. Okay, so now we're going to go to our sort of elementary searches for graphs. So we have depth first and breadth first search. So what you should understand for this one is sort of how they work and what data structures they use to be implemented, and you also need to know what they're good for. So here I have some nice trees here. So I'll go through depth first search first, actually, because it appears first here. Okay, so depth first search basically says go as far as you can from the start until you hit like a wall. So if you imagine if you're exploring a maze, if you want to find if there's exists a path, so is it connected or is there connectability to the end from your starting position? One one strategy could be run as far as you can in a certain direction, and then if you hit a wall, come back, and then try in the other direction, and then but keep doing that at relative, like, so you can yeah, so if you're like in a maze, something like this, like you want to get here and you're here, like you might try going here and you get stuck, but then you go back to the start, go back up, and then perhaps you can stop here, and then you can go from here, you can go up from here, and you can go to the right from here. So it's basically saying you go as far as you can and you just sort of explore everything potentially, until you hit the end. So you're just trying all possibilities. That's more best described here, but in terms of solving a maze, that's one way you can do that. So in terms of this actual structure here, which is easier to see. So for depth first search, you're just going to start at 0, and then you're going to go all the way down until you can't go down. So we're going to go all the way down to 3. And then once we're at 3, there's nowhere else to go. So then we go back up 1 level. We go at 1, and then we go down from 1. Then we go back up to 1, and then we go back up to 0, and then we go the other way. So we explore all this first, and then we go all the way here. And then we do that. And then we go back up, and then we do that. So that's depth first search. And that uses recursion, like for going back. Or it uses a stack. You can do it iteratively, but you have to use a stack data structure. Yeah, so explores as far as possible along the branch before backtracking if it hits a wall. So we use this for detecting cycles, topological sort, and pathfinding mazes, which I tried to explain here. Which I'll explain topological sort in the next slide. But there's another way we could, so that visits all the nodes from the source. There's another way we can also do this. Perhaps instead of going all the way down, perhaps we sort of do it in layers. So that's breadth first search, BFS. So this uses a queue. So what we do here is we have this graph, and then we go down, and then we put all the vertices on this level in a queue. So we're going to visit layer by layer. So we go here first. And then those are in a queue. And then, so we go 0, 1, 2. And then we're going to see, what's in 1. And then we're going to see what 1 is connected to. So then we visit 3, 4. And then there's nothing left. And then we do the other layer here, 5, 6. So that splits it sort of horizontally, or at least in this example, horizontally, so in layers. Yeah, so explores all the neighbors before moving to the next level. So this actually can be used for shortest paths in unweighted graphs. It can also be used, and actually this was a question from the last year exam. It was a multiple choice. Yeah, we had multiple choice last year. It asks if you could use BFS for a weighted graph, where it could also be used where the weights, so I'm going to do weights, are equal. So basically the question was asking, could you use BFS to find the shortest path where all the weights were 10. And that's true because if all the weights are equal, then sort of the weights have no meaning. So the shortest path is sort of derived from breadth first search because since we're going level by level, like we're not going all the way down like depth first search. Like we're just going level by level. Once we hit the level that we're trying to get to, then that's the shortest path. And if all the weights are equal, you can sort of show that the weights don't matter. But yeah, you can use breadth first search in an unweighted graph, or you can use it in a weighted graph where all the weights are equal and 10. If you have negative weights, then you might have negative cycles. So negative weights, you can't, but if they're positive and they're all equal, you can use breadth first search on a directed graph. Or undirected too. Yeah, we also call this level order traversal. And yeah, for both of these, they're going to be E plus V time. Sort of convince yourself that we're only going to be checking what we haven't seen, right? So we're keeping track of where we are. So we're only going to go to V vertices, and we are going to be checking E edges. And so that is true for both of them. So we just get the sum of the two. Yeah. Okay, so topological sort. So a lot of times graphs can be like a representation of dependency or scheduling. So perhaps you want to get to this result here, where you have a scenario. Again, this might be something to look out for. If you're given a graph problem, maybe look out if the problem is signaling something about, oh, there's scheduling, or maybe there's this has to happen before this. Look for those sort of keywords. You might have to use something about topological sort. Maybe you might just have to use it in a relatively similar problem, and you just have to reference the time complexity. Yeah, so it's used for scheduling and dependencies, and it's only defined for DAGs because one, we need direction because dependency implies that we have to do this and then we go here. We can't go back and forth. Like it's a process. We just go forward. And like we don't have like 3 can go to 2 or something like that. So you have linear sort of, you do this, or you can do go here, jump there, sort of thing. Yeah, and then the acyclic part, for dependencies, we're not going to go in a circle, do the same thing over and over again. Dependencies is, you do this, and then you do this. Dependencies would get stuck in cycles. So that's why we needed DAGs, as I explained here. So this is sort of the steps. I don't think you'll have to know all the steps, but I think what you should know is the time complexity. I believe it's on your cheat sheet, and just know what you use topological sort for. So basically, topological sort will turn your graph into this task scheduling graph here. So, and these are the steps here. So again, we use depth first search. And then we add the vertex to the list after all neighbors are visited, and then we reverse it for the ordering. Again, these steps, I wouldn't be too worried about understanding them. Again, it's always best if you do, but I think more so it's just understanding what topological sort is used for. So it's used for dependencies. And then, yeah, I think that's the more important part. I think that's just the more important part for this course, just knowing what to use what algorithm for what problem. That's something you'll be doing for, that's what software engineers do. They pick the right tool for the right job. So that's a very important just thing to carry from this course, is you're learning how to pick the right thing for the right task. Okay, so now we're going to go into minimum spanning tree, or MST. So this is the MST for this graph. So the grayed out ones is like the original graph. So if you put together all the grayed out ones, you get the original graph. And then the dark line is the MST. So the MST is, it's a tree. So again, trees are acyclic. And they're spanning. So it includes all the vertices. And then we're going to have v minus 1 edges. But the minimum spanning tree is saying, what is the tree that, or like, how can I connect this graph with the minimum total cost with no cycles? And it's in an undirected graph. Yeah, so this is, we're sort of minimizing. So if you have if you have edges in the minimum spanning tree, this is going to minimize the sum of the weights of those edges. So the MST is often unique, but it's not necessarily unique. It can be unique if, or it can be inunique if a lot of the edges are the same value. You can have multiple MSTs, but if the edges are all randomly chosen values, there's a good chance the MST is unique. Again, it's only defined for undirected connected graphs. So it has to be connected, because how can you create a tree that connects all the vertices together in a minimum fashion if you can't get from any vertice from any vertice? So the graph has to be connected. If the graph is not connected, it's just a little extra thing. If the graph's not connected, and perhaps you have multiple connected components, the MST algorithm would only calculate the minimum spanning connected component and not for the entire graph. So, yeah, for the entire graph, it has to be connected. Otherwise, it's going to connect the minimum spanning tree for the connected component. Again, why does this matter? Why are we studying it? This comes up a lot in network design, or in railway costs. How can we connect this network without in the least amount of money or power? Those are very important problems. And the applications of graphs are endless. These are just two of them. Yeah, the graphs are also used in, I believe, in biology. I forget exactly where, but I know they also, for medical contexts too, MSTs also appear a lot. And there's two ways you can compute the MST, or there's multiple ways, but there's two popular algorithms. So you have Prim's algorithm and Kruskal's algorithm. So they're both what we call greedy algorithms. You might explore greedy algorithms. Again, I think 2xc3 might be a bit different this year, but we did talk about greedy algorithms a lot in 2xc3 last year, and you'll definitely talk about them in 3ac3. But I wouldn't worry too much about the definitions of greedy algorithms. Just know what a greedy strategy is, not too much about proving that it's greedy or something like that. Just know that it is a greedy algorithm. and we'll go into a bit why that is. Okay, so Prim's algorithm. So again, I left out the proof for the cut property, but this all can happen because of the cut property. So basically, the cut property says that if you have a graph, at least for Prim's algorithm, if you take a cut, so basically if you're at some vertice S, that's part of your like the start of your growing tree. If you take the minimum edge there, you're guaranteed that can be in the MST. Again, there's a whole proof for the cut property, but Prim's algorithm is only possible through the cut property. And then greedy strategy. Greedy essentially is just saying we're going to take, how do I put it? We're going to take like the optimum sort of result for like the current iteration of the algorithm. So we're always taking the minimum weight. So that's optimization minimum. So we're taking the minimum weight edge. Because again, our goal is to create the minimum sum of weights in our tree. Yes, these are the steps. Again, I don't think you have to know all the steps. I think you more so just need to know what is a minimum spanning tree. Actually, it might actually be a good idea to know how to do Prim's algorithm. Last year we had a question where it was just run Prim's algorithm on a graph and then draw out the graph, draw out the MST. So actually, yeah. Essentially, it's just the cut property. So we're going to start at vertex S. Do you think like... I don't think you'll be asked to prove the cut property because again, you can just put that on your formula sheet. I think more so, they might just ask you to, again, you can put a lot of things on your formula sheet, but I think a better question would just be to run Prim's algorithm on a graph or to apply Prim's algorithm like you're given sort of a problem and then you have to convert that to a graph in which you run Prim's algorithm on. That's also a problem that might happen. Again, you could also just write the steps for Prim's algorithm, which I suggest you do. But proving cut property, I feel like that wouldn't be. It could be. But I feel like that's just covered in the lecture. I don't know. I can't really say, but I think a better question is just to compute an MST. Yeah. Yeah. So here we're just repeatedly selecting the minimum minimum weight edge, that we can connect our growing tree from the non-tree, and then we add that edge. So again, you can have for like the time complexity part of this. I know I went through a big rabbit hole last year. We had an assignment last year for 2xc3 about the time complexity of Prim's algorithm, and a lot of people write it in so many different ways, and they don't elaborate on how they get it. So I'm just gonna put a note here. I did put a note there. So it depends what heaps you're using. So you have Fibonacci heaps. I believe the one on Helling's cheat sheet uses the Fibonacci heap. But the one I'm describing here, this one uses the binary heap. Yeah, this is from ALGS 4. So the whole proof for this is in ALGS 4. I'll leave the link to there. So we're just extracting the minimum weight edge and then push all the edges out of the new vertex into the priority queue. So this will usually be the dominant term, E log V, because usually, this will be the dominant term. Whenever you see the time complexity of prims, always consider what priority queue they're using, or heap. Because you can also see, I believe Hellings writes it as, he writes it as v log v plus e. I think something like that. Yeah, let me double check that. Yeah, no, on your cheat sheet's different. I wouldn't really worry about what's actually put on your cheat sheet. Just be more aware of what Prim's algorithm is doing, like the steps. The steps will be relatively the same. It's just the data structure you use will change the time complexity. Yeah, let me, 1 second, I'm just pulling up your formula sheet. Yeah, he writes it as this. Yeah, that's using the Fibonacci heap. Helling's version uses the Fibonacci. Yes, that's one of the algorithms you can use. Another one is Kruskal's algorithm, which I think, personally, I find it a bit cooler. Because it uses a data structure called, it's a bunch of different names you call it. Some people call it union find. More commonly, you'll see it as disjoint set. So the disjoint set data structure, well, it's so sort of self-explanatory. It lets you create disjoint sets. So that will be helpful because we want to see. Okay, so let's just go through Kruskal's algorithm. So first, we're going to sort all edges by weight. So that's different in this algorithm. We're going to sort them by weight from smallest to biggest. And then we're going to create a forest. So each vertex is a separate tree. So that's going to be in our disjoint set. Yeah, so we just initialize the disjoint set. And then for each edge, basically the disjoint set data structure, it can tell you if those vertices are connected or not connected. So if they are in different trees, if we're not connected yet, we can add the edge to the MST and then merge them through union. So this actually has a dot union method that will merge them. Yeah, and we know we can actually just add the edge because, again, we sort it by smallest to biggest edges. And then we can also check through the disjoint data structure if they are already connected, so we skip it. And that will prevent cycles, because if they're already connected and we add them, then we're going to create a cycle. And by the definition of the minimum spanning tree, we don't want any cycles. So that's why we skip there. Yeah, and then we're just going to do this v minus 1 times. Because that's how many edges the tree will have. And yeah, that's the algorithm. So using the disjoint set, we can do these operations very efficiently. Did you guys talk about the disjoint set in class? Yeah, I'm not sure if I can record the practice exam and post it on YouTube, But yeah, we can go over it, not recorded. Yeah. Yeah, I'll see. I think I'm just gonna publish this recording as soon as possible. So yeah. I I don't know what to think of like publishing questions online. I don't think the professors check. So yeah, I don't think it's a big problem. But I know Helms has a bit of a strict policy on it. That's why I'm a bit wary of it. So, okay. Yeah, so the disjoint data set. So again, we were talking about amortized time. So we're going to be doing a sequence of unions and then checking if things are already connected. So that those are sequences of operation. So it turns out this disjoint set, this is basically, yeah, so these operations, these are essentially constant. Like they're approximately constant time, which is amazing. So these happen in constant time. There's a whole proof of it, and they write it, it's a very fancy thing. It's like they write it as this of alpha n, and then this is called like Ackermann time, and basically Ackermann or reverse Ackermann time. It's just a cool thing about why Kruskal's is so efficient is because it's because the disjoint set data structure. So this is called reverse Ackermann time, and this function, it's just a function that's basically it's so much slower than log n. Like this is probably the most efficient data structure I've seen. Like this reverse Ackermann function, and for this disjoint set. So yeah, that's something to consider. But again, it's e log e time, while this one is e log v time. So depending if you're on sparse or dense graphs, you choose accordingly. Yeah. So you have estimate time on when we'll start. Yeah, I realized I went way over time. I was a bit ambitious with doing sort of the full course. Yeah, Hakeem, are you there right now?
Yep.
Go ahead. I think we're gonna do like some practice questions from their practice final. If you want to, do you think you can go over those? I can send you the things with the solutions so you can have them on the side too.
Yeah, sure. Yeah.
All right, thanks. Okay, yeah. I'm just gonna give you my remarks. So I'm just gonna say like what's next in COMPSCI 3. You're gonna do a lot more. You're gonna explore more practical stuff. I'm just gonna go through this quickly. So dynamic programming, backtracking, and then you're gonna do much more deeper stuff in 3C3. I'll just give my tips for the exam. And I'm going to stop the recording, and then I'm going to do a new recording, and I'll debate if I post that one. I'll see. I probably will. Yeah, so my tips for the exam, I have 4 of them. So again, as engineers, your goal is to identify what class problem you have, and then you need to pick what algorithm or solution you have. So if you're doing sorting algorithms, then you can you just focus on, okay, what are my options for sorting? What's my options for graphs? What assumptions do I have? What constraints do I have? So identifying the problem, that's my first tip. And then my second one, since you have the cheat sheet, last year we had a textbook. So textbook, we couldn't control what's in it, but we had the whole course. Basically, you guys can control what is on your cheat sheet, which I think is very powerful. So you can, I would probably suggest you put, if space permits, put some answers to the practice exam on your cheat sheet. So in worst case, because I'm predicting it's going to be very similar, so in worst case you can try to pattern match your questions. Okay, so then your cheat sheet, yeah, your cheat sheet will come in very handy. Like, write things that are not on your reference sheet or your formula sheet. So yeah, it can be steps to algorithms, can be, you can put the cut property on the cheat sheet if you're concerned about that. You can choose what you want. You can put, I don't know if there's been talk about certain questions coming, but you can just customize it to what you think will be on the exam. Yeah, I think it's a good idea to discuss that in the chat, like in the channels. Some people might know more. Maybe you guys can. I'm pretty sure it's okay to share cheat sheets. But if that is not okay, then check the syllabus. That's okay. But and then another practical thing is, if you're stuck, just go to a different question. I think I've said this for all the help sessions. It's always better to just try something new and not just stall at a question, because you might just need a break. Sometimes you need a break, which is a bit paradoxical, but sometimes you need to go away from the problem to get a new idea. So just go try something else so you save some time and come back when you have no other options to come back. That's my advice for that. And probably you can start with the question you're most comfortable with. That's another good strategy. Yeah, those are my tips. And then these are my resources I recommend. So Abdul Bari on YouTube, he's my DASA goat. Yeah, it's a YouTube channel. He makes excellent data structure videos. He has a whole playlist. And then Algorithms 4th edition cheat sheet. If you click on this link, you'll have all the time complexities, like everything you need to know, like all the time complexities, all the formulas, everything. That's from the Algorithms 4th edition textbook. This is the textbook we used last year. And I believe Hellings also uses this textbook too. At least he says he does in the syllabus. This is one of the textbooks for this course. Yeah. Yeah, for me, good luck. You're really close to the finish line. For second year, first semester is probably one of the hardest semesters, especially with 2LC3. So you guys are so close. Keep pushing. Everything's going to be smooth. Yeah, I know I was really scared last year, but I think everything will be okay. Yeah, no, it's a bit scary, especially 2LC3, but yeah. It's a good chance you guys will pass. It's especially Hellings. I think Hellings is a really nice guy. I think, yeah, this course is gonna go well for you guys. So, yeah. So yeah, good luck. And now I'm gonna stop the recording and we'll go through the practice exam. Yeah. Oh yeah, and then for the content I didn't cover, I'm gonna quickly finish the slides, or actually I'm gonna source you other slides from Algorithms 4 that you can use to study for the other concepts. So yeah, because I know I didn't go over linear probing and stuff like that, all the search stuff, but yeah, I think my tips will be, yeah, those are my tips.